want to thank the organizers for giving us the opportunity to present this paper. So this paper is titled Bias In, Bias Out, Evaluating the Folk Wisdom. I'm Jonathan Roth. I'm a postdoc at MSR, and this is joint work with my awesome co-author, Ashesh, who's a graduate student in economics at Harvard. So to motivate this talk, it's well known that algorithms are increasingly playing a role to either aid or replace human decision makers in a wide variety of important domains, from criminal justice settings where they're being used to determine whether a defendant be granted bail, to making hiring decisions, to financial applications, such as whether an applicant should be given a loan or not, to medicine, where algorithms are being used to determine whether a patient should be tested for a given condition, for instance. And of course, there is a common concern that if the humans generating the data used for training these algorithmic decision rules are biased against particular groups, say minorities or women, then there's concern that the algorithmic decision rule will inherit this bias. And so I think this concern is captured nicely in this quote from Barocas and Selp's 2016. They rate the character of the training data can have meaningful consequences. Biased training data leads to discriminatory models. So I think there's a lot of intuition for this bias in, bias out concern. What motivated this paper is that statements about how bias in training data translate to biased algorithmic decision rules are often somewhat imprecise. So what exactly does it mean for the human to be biased in the training data, and through what mechanisms does that translate to the algorithm's treatment of the discriminated against groups? And is it necessarily always the case that discriminatory humans in the training data lead to discriminatory models? In this paper, we sort of try and formalize these questions by analyzing how bias by humans in training data affects algorithms. And we do this through the lens of a classic model of discrimination in economics, going back to work by Gary Becker in the 1950s. So to give you an overview of the key results in this paper, we show that while in some cases the usual bias in, bias out intuition holds, human bias in training data need not necessarily produce discriminatory algorithms. So in particular, that we show that for an important class of prediction exercises, actually naively trained algorithms exhibit what we call bias reversal, which means that the more biased is the human decision maker generating the training data, the more an algorithmic decision rule sort of naively trained on this data is actually favorable to the discriminated against group. And so we then provide a series of results trying to dig in sort of when we get this bias reversal versus when we get the usual bias in, bias out intuition. And so a sort of intuitive summary of our results is that a key question to ask is, does the human bias sort of manifest itself in the data through selection of sort of which units enter the training data, or through mismeasurement of the desired label? So our model that exhibits bias reversal has the first component, selection into training data, whereas I think the usual intuition comes from cases where the bias sort of directly drives a wedge between the measured label and the label that we actually care about. So let me now tell you a little bit more about our setting. So we consider settings where outcomes for the training data are only generated if a potentially biased decision maker takes a particular action. So for instance, in a criminal justice setting, we may observe only whether a particular suspect commits a crime if released on bail, if the judge chooses to release that defendant on bail. Likewise, we may only observe the performance of a particular job candidate if the firm decides to hire that candidate, and sort of similar kind of parallels exist in sort of the health and financial settings. This type of setting is what has previously been called the selective labels problem, meaning that we only see a selected group of labels for a set of individuals for whom the decision maker has made a particular action. So let me now try and give you a little bit of intuition for our bias reversal result that I'll then make precise throughout the rest of the talk. We're going to consider settings where training data is only generated if a potentially racially biased decision maker takes a particular action. So for your example, you can think that we may only observe job performance for a particular worker if that candidate is hired. And then individuals in our training data will be selected on factors that are both observed by some factors that are observed by the decision maker, but not by the data scientist. So for example, the hiring manager may make decisions based on hard information, such as the candidate's degree and their experience, which would be given to the algorithm, but also potentially based on soft information, such as how the candidate acts in interviews that may be predictive of their productivity, but may not be recorded in the information given to the data scientist. And so in general, the people who get hired are going to be positively selected on this soft information that's not observed by the algorithm. But this effect is going to be even larger for the minority group. The more biased is the hiring manager. So if the hiring manager is really racially biased, for instance, then the only blacks who enter the training data are going to be blacks who have generally have very good soft information. And so as a result, the algorithm is going to learn based on this selected group of data that blacks are actually extremely productive. And so the more biased is the hiring manager, the more the algorithm decision rule trained on this selected data is going to recommend to hire minorities. So I think this example sort of nicely illustrates the intuition behind our results. Since our application in the paper is going to be to data from the New York Stop and Frisk program, which related to police searches, we're going to sort of frame our model in the context of police searches. So let me now, to provide some additional information, just kind of go through quickly the exact same type of intuition in the context of police searches. So we're only going to observe whether a suspect is carrying contraband or not if they're searched by the police. The police officers are again going to base their decisions based on hard information given to the algorithm, such as the demographics of the suspect and the location of the stop, as well as potentially soft information, such as their behavior during the stop that may not be recorded in the data. And so then in general, the people who are searched by the officers are going to be selected on soft information that's indicative of them carrying contraband. However, the more biased are the officers against blacks, say, the less there is selection on this soft information for the minority group. So for example, in the extreme case where the officers are incredibly biased and search almost all blacks, there's basically no selection on this soft information. And thus, as a result, the more biased are the officers, the lower is going to be this sort of rate of carrying contraband among the search sample. And therefore, the algorithm is going to recommend searching fewer minorities. I've now given you the intuition as a roadmap for the remainder of this talk. I'll talk about the model. I'll show you some simulations based on this New York Stop and Frisk data, and then I'll conclude with some discussion of the implications and limitations of our results. So let me start with the model. So we're going to have a model of biased police search decisions where police officers wish to search individuals with a high probability of carrying contraband. And police officers are going to be what's called taste-based discriminators against African Americans. So they're going to act as if there's sort of an additional benefit or a reduced cost of searching African Americans. And then the data on conducted searches are going to be revealed to the data scientist. This is going to have the selected labels problem in the sense that we're only going to see the outcome of a search for conducted searches. And then we're going to think of there being a data scientist who wishes to predict which individuals that are stopped are the most likely to be carrying contraband, for instance, with the goal of determining whom should we search in the future. And so then the goal of the model is then going to be to evaluate how officer bias against blacks affects the sort of performance of a naive prediction function produced by the data scientist on this selected data. So for notation, we're going to have individuals who are characterized by Y, X, R, and U. So Y is going to be a binary indicator for is the person carrying contraband. R is going to be their race with R equals 1 for African Americans. And then we're going to have some features, X, which are going to be observed by the algorithm. And then we're going to have this variable U, which is going to represent additional factors that are observed to the police officer during the stop, but that are not recorded in the data and thus aren't observed by the data scientists. And so we're going to think of our police officer as deciding to search if the probability of carrying contraband exceeds a race-specific threshold. So we're going to have S, which is a function of X, U, and R, be an indicator for whether the police search, and this is just going to be determined by a threshold rule where we take the probability that the individual is carrying contraband, and then we compare that to a threshold, and the threshold used is going to be C0, the threshold for whites, minus tau times R. So if tau is positive, police apply a sort of lower probability threshold for the minority group, and therefore they're racially biased. And this sort of threshold search rule sort of comes out of a expected utility maximizing behavior if the police officers are sort of have utility from catching people who are carrying contraband, but perceive either an increased benefit or a lower cost from searching blacks who rather than searching whites. Okay. So given these selective labels, you might think of sort of a few naive ways that the data scientist may train an algorithm. So the first is just to sort of subset to our sample for which we observe the label Y. And so to just predict Y among the search sample, which we'll denote by S equals 1. An alternative exercise you might think about is if you have data on the characteristics of the individuals who are not searched, but you don't have their outcomes, then you might, instead of predicting the label of interest Y, you might predict the officer decision itself on the full sample, so you predict S. And then finally, you might impute the outcome to be missing. You might impute the outcome to be 0 for the cases where it's missing. So say that an individual is carrying contraband if and only if they're both stopped by the searched by the police and found to be carrying contraband. So that would be predicting this sort of compound outcome Y times S. And so in this talk, we're going to sort of extract away from sort of estimation error of these algorithms and evaluate the properties of sort of the optimal prediction function under squared laws, which is just the conditional expectation. So for instance, we're going to think about for the first prediction exercise, we're going to think about predicting Y given X and R in the search sample, whereas for the other exercises, we're going to think about predicting, for instance, S given X and R, or Y times S given X and R. And you'll notice here that for now, we're going to consider the case where R is explicitly included in the algorithm. I'll talk a bit later briefly about sort of extensions we have where R race is not directly included in the algorithm. Okay. So I'm now ready to get to you to sort of our key bias reversal result. So this result says, suppose we train an algorithm to predict Y in the search sample. So we're going to denote Y hat S equals 1 as a function of X and R to be the predicted value of Y given that value of the covariance X, the race R, and the fact that we're conditioning on the individual being in the search sample. So this is the result. This is the sort of resulting prediction from our algorithm trained to predict the label in the sample for which that label is available. And so this result says that predictions for the minority group with feature X, so Y hat of X and R equals 1, are decreasing in tau for all x and tau, such that the individuals enter the data with positive probability. So this says the more racially biased are the officers, the larger is tau, the lower is the predicted risk for blacks with sort of any fixed characteristics that are observed by the data scientist. And so a corollary of this result is that if we were to calibrate an automated search rule that searches individuals if and only if their predicted risk is larger than some threshold, then the fraction of African Americans searched under the automated rule would be decreasing in the bias of the officer's tau. So to just kind of quickly go over the intuition for this result, we have that police officers incorporate this unobservable U into their search decision. The search individuals tend to have higher than average values of U relative to the population. And so in general, we're going to tend to overpredict Y for any given value of X from training on this selected sample. However, as police become more biased, then selection on U becomes less severe for African Americans because they're more likely to search any given African American. So for example, in the extreme case where this discrimination parameter is larger than the cost for whites, the police search all African Americans, and so there's no selection at all on U for African Americans. So that was sort of the kind of unintuitive result that we have for bias reversal. Now let me show you about sort of small changes to our model where we change the prediction exercise, and then we can recover sort of the usual bias in, bias out intuition. So if instead of predicting the label Y in the search sample, we either predict S, which is just the officer decision, or we impute the outcome to be 0 if the individual is in search. Well, in this case, if we predict either Y times S or just S, then we get the usual bias in, bias out prediction. So in particular, we find that these predictions Y hat times S or S hat are increasing in tau for all X and tau, and consequently the fraction of individuals in the minority group that are searched under an algorithmic decision rule that's based on a threshold for Y hat S or S hat is increasing in tau. So here we actually get the usual bias in, bias out result. So to kind of summarize the results of these 3 exercises, if we predict the label of interest in the selected sample, then we get bias reversal. Whereas if we predict either the officer decision or this imputed label in the full sample, we get the usual bias in, bias out type of inheritance results. So what differs between these 2 classes of exercise? Well, in the first exercise, the outcome of interest Y is properly measured, but the human bias affects the sample used for training. In contrast, in the later 2 exercises, the sample remains constant, but the increase in bias produces a larger wedge between what is sort of the label used in training, either S or Y times S, and the label that we actually care about, Y. So depending on whether the human bias is affecting the selection into the data or the label of interest, then we sort of get these opposite results. And you can, of course, imagine cases where the human bias affects both of these things, in which case we sort of may have a horse race between these 2 types of effects. Great. So in the interest of time, I'm just going to briefly talk about 3 extensions that we have in the paper, but not go into much detail. So far, I've presented to you a model where the police base their decision based on basically the optimal forecast of risks for individuals with a given set of features. We show that these results are robust to allowing for somewhat independent noise in their assessments of the individual's risk. We've also presented results so far where race is explicitly included in the algorithm. We also consider the case where race may be excluded from the algorithm. The results sort of trivially go through, if you exclude race from the algorithm, if race is reconstructible from the other features. We show if race is not reconstructible from the other features, then these results may or may not go through, depending on whether this sort of a marginally searched minority, when discrimination increases, has features that look more like the average black or the average white. And then finally, in the example that I've showed you so far, the more biased are police officers, the more labels in the training data are generated for the minority group. But in other settings, such as college admissions or hiring, the opposite is true. So the more discriminatory are the humans, the fewer labels are generated for the minority group. And we show that similar types of comparative statics exist in these settings as well. So now let me briefly talk about our simulations. So we're going to use data on police searches conducted as part of the New York City Stop and Frisk program. So our data is going to contain information on over 350,000 police searches. And we're going to have demographic information about each of the stops, as well as the officer's stated reason for the stop, such as carrying a suspicious object. We're going to treat sort of the stated reason for the stop as something that seems sort of like an unobservable that may, in theory, not be included in the data. And so for the purposes of our simulation, we're going to treat that as a unobservable that's not given to the algorithm. And so to overview our simulation design, what we're going to do is we're going to start with the data set of searches that were actually conducted, and then we're going to create synthetic data sets with varying degrees of racial bias by selectively undoing searches that actually happened in reality. And we're going to determine who to unsearch by creating a predictor of carrying contraband, and then pretending that those with predicted risk below a certain race-dependent threshold were not actually searched. So I'm going to, I think in the interest of time, I'm going to skip the technical details of the simulation design and just skip ahead to the results. So what we have here is a plot where on the x-axis, we're going to plot tau, so how discriminatory are the officers in the simulation, with larger values of tau corresponding with more discriminatory officers. And then on the y-axis, we're going to have the probability that a black falls in the top half of predicted risk by the trained algorithm. So basically, we're going to search the top half of people by algorithmic predicted risk. This would be the fraction of blacks that get searched. And so the blue triangles illustrate our bias reversal result and show in particular that the larger is this Becker's tau, the fewer fraction of African Americans are searched by this rule. By contrast, if we predict the officer decision S, or we predict this imputed label Y times S, then we see that the usual bias in, bias out intuition holds, meaning that the larger is the officer's discrimination, the more blacks are searched under this automated rule. So let me wrap up by just talking a bit about the implications of this work. So our paper is certainly not meant to imply that concerns about algorithmic bias are not valid. But what we think our results do imply is that discussions about how human bias affects algorithmic decision rules should be a bit more nuanced, and particular attention should be paid to how the human bias influences the training data. So in particular, we've shown that when the human bias influences the training data via selection into the data, we may actually get bias reversal, whereas the usual intuition comes from when the human bias sort of affects bias in the measured label. And we can, of course, think about settings where both of these potentially hold. And then finally, our results suggest that settings where humans are acting sort of benevolently to minority groups may actually be of concern, because sort of playing our results in reverse, they sort of suggest that in those cases, the algorithm may actually learn that the outcomes for blacks are not actually so good in the training data and want to, say, admit fewer blacks into college. And so then finally, there are several limitations and possible avenues for future research in our paper. So we're going to consider only taste-based discrimination, but you could imagine thinking about other forms of discrimination as well. We abstract away from sort of finite sample considerations of actually estimating the algorithm, which could potentially be important. And one feature of our paper is that we don't actually take a stand on what's sort of objectively fair. We only sort of describe comparative statics of how the algorithm treats minorities under more or less discriminatory regimes. And then finally, we sort of consider a static model, but you might imagine situations where the algorithm is sort of initially trained in a given period, but then updated based on more data. So thank you, everyone, for listening and for giving us the opportunity to present this work. Thanks.